Have you ever felt like trying to manage and deploy modern applications is like, I don't know, like wrangling a herd of cats?
Haha, I can see that, especially with all the moving pieces and potential points of failure.
Exactly. And to make things even more complex, you've sent us a bunch of really interesting transcripts this time from various online videos, actually.
Yes, I see. Let me guess. Sublime a Techie on Tech Unplugged.
You got it.
Always a good source for deep dives on complex technical topics. Plenty to unpack there.
For sure. So what we're going to try to do in this deep dive is, well, go on that journey together, from simple containers with Docker all the way to the sometimes mind-bending world of Kubernetes orchestration.
Right. And we'll really focus on making sure we understand not just what these technologies are, but why they came to be so important in the first place.
Sounds good. So let's start at the beginning with Docker. What problem was Docker really created to solve?
Well, imagine you're a developer, right? You've built this awesome app, and it runs perfectly on your laptop. But then,
But then you try to deploy it to a server, and it's like a completely different beast. Nothing works the way it's supposed to.
exactly. Inconsistent environments used to be a huge headache for developers. Different operating systems, missing libraries, conflicting dependencies. It was a constant source of frustration.
So Docker swoops in to save the day, like a superhero of software development.
In a way, yes.
Uh-huh.
It provided a way to package an application and all its dependencies into a single portable unit. We call that a container.
Okay, so it's like this self-contained box that holds everything your app needs to run, no matter where it goes.
That's a great analogy. And the way you define this container, it's all laid out in a Docker file.
Ah, yes, the Docker file. It's like a recipe for building your Docker image.
Precisely. It's a text file with all the instructions needed to build a Docker image. And this image is essentially a snapshot of your application and its dependencies, ready to be run in a container.
And you can run multiple isolated containers from that single image. That's pretty efficient.
It is. And it solves that problem of inconsistent environments because now you have a guaranteed consistent runtime across development, testing, and production.
Right, so Dockerizing a project becomes this key step in the development process. You build your Docker image, and boom, you have this portable, consistent unit of your application. Sublime Techie calls it the foundation of modern development.
And he's not wrong, though he does have a lot to say about multi-stage Docker builds, too, which are really interesting.
Yes, multi-stage builds. Tell me more about that.
Well, initially, Docker images could get quite large because they'd include all sorts of things, development tools, build artifacts, things you don't actually need to run the application in production.
So it's like carrying around this extra baggage that slowed things down and took up unnecessary space.
Right. And multi-stage builds are a way to optimize that. You can have multiple stages in your Docker file, one for building and one for the final lean production image. Only the essentials get carried over.
Okay, so it's like having a separate workshop where you build and assemble everything, and then you just take the finished product and leave the tools behind. Makes a lot of sense.
Exactly. And the result is smaller images, faster deployments, and a more efficient overall process.
So we've got these neat little Docker containers all packaged up and ready to go. But then things start to get more complicated.
How so?
Well, what happens when you have not just one or two containers, but maybe dozens, hundreds, or even thousands of them running simultaneously?
Yeah, that's when things get really interesting and you start needing a more powerful solution to manage all of that complexity. That's where Kubernetes comes in.
Kubernetes, the superhero of container orchestration.
You could say that. Kubernetes is all about automating the deployment, scaling, and management of containerized applications. It helps you manage those large, complex deployments that would be a nightmare to handle manually.
So if Docker is about packaging, Kubernetes is about conducting the orchestra, making sure all the containers play together nicely at the right time, at the right volume.
That's a great way to put it. But it's important to remember that, as Sublime Techie pointed out, Kubernetes isn't always the answer.
Right, he made that point pretty clearly. It can be overkill for smaller projects.
Exactly. For small applications with just a handful of containers, the overhead of setting up and managing Kubernetes might not be worth it. You might be better off with simpler tools like Docker Compose, at least initially.
So it's important to assess the scale and complexity of your application before diving headfirst into the Kubernetes world.
Absolutely. But assuming we've determined that Kubernetes is the right tool for the job, let's talk about the core concepts. Where should we start?
Well, Sublime Techie dives pretty deep into pods, which seem to be fundamental.
Right, pods. They're the smallest deployable unit in Kubernetes. Think of a pod as a group of one or more containers that are always deployed together on the same host.
So they're like inseparable buddies, always hanging out on the same machine, sharing resources like network and storage.
Exactly. And there are a couple of ways to create these pods. You can use imperative commands or declarative manifests.
Ah, yes, the imperative versus declarative approaches, a classic debate.
Uh-huh, it is. The imperative approach is like giving direct orders. You use kubectl commands like kubectl run to create and manage pods on the fly. It's useful for quick tasks and experimentation.
But it can get messy and hard to track, especially for more complex deployments, right?
Yeah, that's where the declarative approach comes in. You define your desired state in a YAML manifest file, and Kubernetes takes care of making it happen. It's more reproducible and gives you a clear record of your configuration.
Okay, so these YAML manifests are like blueprints for Kubernetes objects. What does a typical pod manifest look like?
Well, you'll always have at least four main sections: APA version, kind, metadata, and spec.
So APA version specifies which version of the Kubernetes API you're using. Kind indicates the type of object, which in this case would be pod. Metadata holds identifying information like the pod's name. And spec is where you define the actual specifications for the pod.
Exactly. Within spec, you'd specify the containers to run, the images to use, any resource requirements, and so on. It's all very structured and well-defined.
And once you have your pods up and running, you need ways to interact with them. Sublime Nikki spent quite a bit of time on the essential kubectl commands.
Right. Commands like kubectl get pods to list all your pods, kubectl describe pod to get detailed information about a specific pod, kubectl delete pod to remove a pod, kubectl apply to create or update resources based on your YAML manifests, and kubectl logs to view the logs of your containers.
So it's your command line toolbox for managing all things pods. He also mentioned readiness probes, which are like little health checks to make sure your containers are actually ready to work.
Yes, readiness probes are crucial for ensuring that only healthy and ready pods receive traffic. They help you avoid sending requests to containers that are still starting up or having issues. And of course, he covered troubleshooting too.
Yes, like the dreaded image pullback off error, which can be a real pain.
Oh yeah, that one means Kubernetes is having trouble pulling the container image from your registry. Could be a typo in the image name, an issue with credentials, or a problem with the registry itself.
Okay, so we've got our pods, and we know how to manage them, but what about ensuring that we always have a certain number of them running? Like, what if a pod fails unexpectedly? That sounds like a recipe for downtime.
That's where replica sets come into play. A replica set's job is to ensure that a specified number of replica pods are always running.
So it's like an auto-healing mechanism. If a pod dies, the replica set automatically spins up a new one to take its place.
Exactly. And then, building on top of replica sets, we have deployments, which provide even more sophisticated management capabilities.
Deployments. They sound powerful.
They are. Deployments manage replica sets and provide a declarative way to handle updates and rollbacks. You can perform rolling updates with zero downtime, meaning your application stays available even while you're deploying changes.
So it's like swapping out the engine of a plane while it's still in flight. Seamless transitions, no interruptions.
That's the goal. And if something goes wrong with an update, deployments make it easy to roll back to a previous working version. Very handy for keeping things stable.
Now, one thing I'm curious about, pods themselves can be created and destroyed pretty dynamically, right? So how do we give them a stable network address, a way for other applications to reliably find and communicate with them?
That's where services come in. Services provide a stable endpoint for accessing a group of pods, even if those individual pods are changing.
So it's like a virtual front desk that directs traffic to the right place, regardless of who's currently manning the desks behind the scenes.
I like that. Services abstract away the dynamic nature of pods and provide a consistent way to access your application.
And there are different types of services, right? Sublimeski went through quite a few. Cluster IP, node port, load balancer, and external name.
Yes, each type serves a different purpose. Cluster IP is the most basic. It exposes the service on an internal IP address, only accessible within the Kubernetes cluster itself. It's great for internal communication between different parts of your application.
So cluster IP keeps things private, like an internal phone system within a company.
Right. Then we have node port, which exposes the service on a specific port on each node's IP address. This allows you to access the service from outside the cluster.
So it's like publishing a phone number that rings on every desk in the office so anyone outside can call in.
Exactly. It's a straightforward way to make your application externally accessible. But for more robust and scalable external access, you typically use a load balancer service.
Load balancer sounds like the big leagues.
It is. When you create a load balancer service, if you're running on a cloud platform, your cloud provider will typically provision a load balancer that distributes incoming traffic across your nodes and then to your pods.
So it's like having a dedicated receptionist who handles all the incoming calls and routes them efficiently.
Precisely. And this usually gives you a public IP address or DNS name so you can easily access your application from the internet. Though it is important to remember that with Kind, for local development, you won't usually get a full external load balancer.
Right. That's a good point to remember. Now, there's one more type of service we haven't talked about yet, external name.
Ah, yes, external name's a bit different. It allows you to map a service in your cluster to a DNS name that exists outside the cluster.
So it's like having a shortcut or alias that points to something external.
Exactly. It's useful for accessing external databases or other services that aren't part of your Kubernetes deployment. And Sublimeticy also showed us a neat trick with the kubectl expose command, a quick way to create a service, often based on an existing deployment or a replica set.
Very handy. Okay, so we've covered the core building blocks: pods, replica sets, deployments, and services. Now, what about organizing resources within a larger Kubernetes cluster?
Ah, that's where namespaces come in. Namespaces allow you to divide your cluster into virtual subclusters, essentially.
So it's like creating separate departments within a company, each with its own resources and responsibilities.
Exactly. It helps with organization, isolation, and resource management. You can have separate namespaces for different teams, projects, or environments like development, staging, and production.
And this way, things are more contained and manageable, and you can apply different policies and quotas to each namespace.
Right. By default, kubectl commands operate within the default namespace. But you can specify a different namespace using the -n flag.
So if you want to see the pods in a namespace called My Project, you would use kubectl get pods -n My Project. Easy enough.
It is. And Sublimeticy showed us that resources in different namespaces can be isolated, but you can also configure them to communicate with each other if needed. So it's a nice balance of separation and connectivity.
Speaking of connectivity, let's move beyond single container pods. What about those scenarios where you need to run multiple containers within the same pod? Sublimeticy called those multi-container pods.
Ah, yes. Multi-container pods are great for situations where you have containers that are tightly coupled and need to share resources and lifecycle. He gave the example of a sidecar container, which might run alongside your main application container.
So a sidecar container is like a little helper that provides additional functionality, like logging, monitoring, or acting as a proxy.
Exactly. And then there are init containers, which run before the main application containers start.
So they're like setup crews that prepare everything before the main event.
Perfect analogy. Init containers are often used for things like initializing data volumes, setting up environment variables, or running pre-start scripts.
Makes sense. Now, what about those situations where you need to make sure a specific pod is running on every node in your cluster?
That's a job for daemon sets. A daemon set ensures that a copy of a pod runs on all or a selected set of nodes.
So it's like having a security guard stationed at every entrance of a building.
Exactly. Daemon sets are commonly used for deploying cluster-wide services like logging agents, monitoring agents, or network plugins. They ensure that every node has the necessary component running.
Sublimeticy also briefly touched on jobs and cron jobs. What are those all about?
Jobs are for running finite tasks that run to completion. Once the task is done, the pods are typically not restarted. Think of it like running a batch script.
So it's like a one-time operation, like a cleanup crew that comes in, does its job, and then leaves.
Yep. And cron jobs are for running jobs on a schedule, like the cron utility in Linux.
Ah, so it's like setting up a recurring calendar event, but for Kubernetes tasks. Run this backup every night at midnight, that sort of thing.
Exactly. Cron jobs are great for automating recurring tasks. Now, moving on, we can also get more specific about where our pods run within the cluster. Sublimeticy talked about static pods and manual scheduling.
Okay, tell me about those.
Static pods are managed directly by the kubelet, which is the Kubernetes agent that runs on each node, rather than by the central Kubernetes control plane.
So they bypass the usual scheduling process. Why would you want to do that?
Well, they're mainly used for bootstrapping critical Kubernetes components themselves, the components that actually make up the control plane. It's a bit of a specialized use case. And then there's manual scheduling, where you explicitly assign a pod to a specific node in the pod's YAML manifest.
So you're basically overriding the default scheduling logic and saying, I want this pod to run here and nowhere else.
Right. It gives you that direct control, but it's not something you'd usually do for most application deployments. It kind of defeats the purpose of Kubernetes automated scheduling and resource management.
Okay, so let's talk about organizing our Kubernetes objects using labels and selectors. It sounds like a powerful way to manage things at scale.
It is. Labels are key value pairs that you can attach to almost any Kubernetes object, like pods, deployments, services, and more.
So it's like adding tags or categories to things so you can easily find and group them.
Precisely. And then you use selectors to target specific sets of objects based on their labels. For example, a service might use the selector to identify the pods it should send traffic to.
So it's like creating filters or search criteria. Show me all the pods with the label environment.production, that kind of thing.
Exactly. And you can view an object's labels using the kubectl get command with the show labels flag. Now, to control where pods get scheduled, we have a couple of mechanisms. Sublime Decky talked about taints and tolerations and also node selectors.
Okay, those sound a bit more complex. Break them down for me.
Sure. Taints are applied to nodes and act like repellents. They prevent pods from being scheduled on those nodes unless the pods have matching tolerations.
So it's a way to say, I don't want just any pod running here, like reserving a VIP area in a club.
I like that. It's useful for dedicating nodes for specific workloads or for isolating certain types of applications. Tolerations, on the other hand, are applied to pods, and they allow those pods to be scheduled on nodes that have specific taints.
So it's like having a special pass that gets you into the VIP area.
Exactly. Node selectors are another way to constrain where pods run. You define node selectors in your pod manifest, specifying the labels that a node must have for the pod to be scheduled there.
So it's a more direct way of saying, I only want this pod to run on nodes with these specific characteristics.
Right. Now, another important topic that Sublime Techie covered is setting resource requests and limits for containers.
Okay, why is that so important?
Well, it's all about ensuring efficient and predictable resource utilization in your cluster. Resource requests tell Kubernetes the minimum amount of CPU and memory that a container needs to run.
So it's like reserving a table at a restaurant. You're guaranteed to have that space when you arrive.
Exactly. The Kubernetes scheduler uses these requests to determine which nodes have enough capacity to run the pod. Limits, on the other hand, set the maximum amount of resources a container can consume.
So it's like setting a budget. You can't spend more than this.
Right. If a container tries to exceed its limits, it might be throttled or even terminated by the operating system's out-of-memory, OOM, killer.
Ouch. So it's important to set sensible limits to prevent one container from hogging all the resources and crashing the whole party.
Absolutely. Now, to help keep our applications healthy and responsive, we have a couple of tools: horizontal and vertical pod autoscalers.
Those sound pretty self-explanatory. Horizontal scales by adding more pods, and vertical scales by giving existing pods more resources.
You got it. The horizontal pod autoscaler, or HPA, automatically adjusts the number of pod replicas based on observed metrics like CPU utilization. So if your application starts getting more traffic, the HPA can automatically spit up more pods to handle the load.
And the vertical pod autoscaler, or VPA, adjusts the resource requests and limits of your pods based on their actual usage patterns. So if a pod consistently needs more memory, the VPA can automatically give it a bigger allowance.
Exactly. And to make sure our containers are actually working as expected, we have liveness and readiness probes.
Ah, yes, those little health checks again.
Right. Liveness probes check if a container is still running and should be restarted if it's not. Readiness probes check if a container is ready to serve traffic and will prevent requests from being sent to containers that are not yet ready.
So liveness is about survival, is it alive? And readiness is about functionality, is it ready to work?
It's a good way to remember it. Now, what about managing configuration details and sensitive information that our applications need? Things like database passwords and API keys.
Ah, the secrets. We don't want those floating around in plain text.
Absolutely not. That's where config maps and secrets come in. Config maps are for storing non-sensitive configuration data, like feature flags or environment settings. You can inject this data into your pods as environment variables or mount it as files.
So it's like a central repository for all those configuration bits and pieces.
Exactly. And secrets are specifically designed for sensitive data like passwords, API keys, and certificates. They're stored in an encoded format for security.
So they're like those little lockboxes you keep your valuables in.
Exactly. And just like config maps, you can inject secrets into your pods as environment variables or mount them as files. The application then has access to that sensitive data without it being directly exposed in the code or configuration files.
Smart. Okay, before we move on to the practical stuff, Sublime Techie spent some time talking about SSLTLS and how important it is in this whole Kubernetes world.
Yes, he's absolutely right. SSL-TLS is essential for secure communication, especially when exposing applications over the internet.
Right, we're talking about HTTPS, the little padlock icon in your browser that assures you a website is secure.
Exactly. SSL-TLS encrypts data in transit, so it can't be intercepted and read by eavesdroppers. It also uses digital certificates to verify the identity of the server you're connecting to, ensure you're talking to who you think you're talking to.
So it's about confidentiality and trust. No snooping and no impersonation.
Exactly. Understanding SSLS is crucial for securing applications running in Kubernetes, especially when dealing with ingress controllers and managing external access to your applications.
Okay, so we've covered a ton of ground on the conceptual side of things. Now let's get practical. Sublime Techie recommends using Kind Kubernetes in Docker as a great way to get hands-on experience.
Kind is fantastic for learning and experimenting with Kubernetes on your local machine. It lets you create lightweight Kubernetes clusters using Docker containers as nodes.
So it's Kubernetes running inside Docker. Kind of meta, but I guess it makes sense.
It does. Setting up a Kind cluster is pretty straightforward. You need Docker installed, then you install the Kind command line tool, and you can create a cluster with a single command. You can have single-node or multi-node clusters.
So you're essentially creating a miniature self-contained Kubernetes environment right on your own computer.
That's it. And once it's running, you interact with it using the kubectl command line tool, just like you would with a production cluster. You'll use commands like get nodes to see the status of your cluster, cluster info to get details, and config use context to switch between different cluster configurations.
And Sublime Techie also mentioned that you might need to configure some port mappings in Kind to make node port services accessible from your machine.
That's right. It's a small configuration tweak, but important if you want to access your applications running in the Kind cluster from your local network.
Wow, that was quite a journey. From those fundamental Docker concepts all the way to the powerful orchestration capabilities of Kubernetes.
And it all builds so logically from one step to the next, solving those initial challenges of inconsistent environments, then tackling the complexities of managing containers at scale.
It's incredible to see how these technologies have evolved to make deploying and running applications smoother and more reliable.
Absolutely.
Yeah.
And it really highlights the collaborative nature of the software development world, people building upon each other's ideas and innovations.
So thinking about this whole journey, from those basic Docker commands to orchestrating complex deployments with Kubernetes, what new insights have you gained about managing applications in this modern cloud-native world?
For me, it's the power of automation and abstraction. Kubernetes takes so much of the heavy lifting off our shoulders, allowing us to focus on building and delivering great applications rather than getting bogged down in the operational details.
That's a great point. And for our listeners who are eager to dive even deeper, what specific areas would you recommend exploring further? What piqued your curiosity during this deep dive?
Well, the Kubernetes scheduler is fascinating. Understanding how it makes those placement decisions for pods is key to optimizing resource utilization. And network policies are another area worth exploring. They provide a way to control how clients can communicate with each other, adding an extra layer of security to your deployments.
Excellent recommendations. And for those who want to get practical, setting up a local Kind cluster and playing around with YAML manifests is a great way to solidify your understanding and gain valuable hands-on experience.
Absolutely. The cloud-native landscape is vast and constantly evolving, so there's always something new to learn and explore.
Well said. Thanks for joining us on this deep dive.